All right, today we're going to look at our Chapter 18 notes. This is over exponential functions. Everything from this chapter should be reviewed from Algebra 1, where you looked at exponential functions in a great deal. We're just going to review it a little bit here. So first thing I'm going to do is I'm going to go through how to graph 3 of these. I highly recommend anytime you're graphing that you utilize your graphing calculator, at least as a double checking device. So my y equals, I'm going to type 3 to the x power and press graph. I'm all zoomed out for my last problem, so I'm going to go back to zoom standard, which is 6. And that looks a little bit better. In order to sketch a graph, second graph brings me to a table where I can plot some points. 1, 3, let's see, probably go a little smaller, 0, 1. -1 is 0.3. If you notice your values, as your values get, x values get smaller, our y values are getting closer to 0. Those are like tiny scientific notation numbers. Eventually I think it says 0. Ooh, maybe not. Okay, they just get smaller and smaller and smaller. Sometimes it'll say 0, depending on the question. But our values are getting smaller and smaller and smaller, but never quite actually reaching 0. And then as we go to the right, as our x values get bigger, our numbers get larger. So 2, 9, and the next one's off the graph. When we draw in our shape, we need to make sure not to cross the x-axis. It goes right along the x-axis, just a little bit above. And then it curves up like this. This is an exponential function. As far as x-intercepts go, this line never crosses, never touches the x-axis. As it goes this direction, it gets closer to the x-axis, but never actually crosses it. So this will have none. For my y-intercept can always be picked out from your table. 0, 1 is where it's crossing the y-axis. I do have an asymptote. Now, an asymptote is a line that our function approaches but does not cross. In this case, we have a horizontal asymptote. So our horizontal asymptote goes right along the x-axis. As our function comes down, it gets very close to the x-axis and it approaches it as x gets very, very small. It does not cross that line. So our asymptote here is a horizontal line of y equals 0. Our domain is a list of all inputs, so we are allowed to input anything we like here. Additionally, our arrow points to the left. It points up, but in actuality also points to the right. So our domain in interval notation is -infinity to infinity. In set notation, it's all x such that x is a real number. Our y's or our range, it's not the same case. So for our range, our function does not go all the way up and all the way down. For our range, our function does not exist down below. So it does not exist lower than 0. If you go low to high, it starts existing at 0 and then goes up to infinity. So our range will be from 0 to infinity. It doesn't include 0 because it never actually reaches 0. It just gets very close to it. And in set notation, it's all y such that y is greater than 0. This is an exponential growth model. In an exponential growth model, our values start out small and they quickly go away from 0. They move away from 0. They get bigger. So they start out close to 0 or small, and then they get bigger as they go. As x gets bigger, our values get larger very, very quickly. So this would be an example of growth. For our next example, we're going to graph y equals parentheses 1/3 to the x power. In order to get specific points to put on our graph, I'm going to press second graph and produce a table and plot some points from this table. So I've got the point negative, oops, that's too big, -2, 9, -1, 3, 0, 1, 1/3, and then they get smaller. Once again, they do approach 0 without actually reaching 0. They just get closer and closer and closer. They get smaller and smaller and smaller. So this comes down like this, and then right across 0. This is an exponential decay model. In an exponential decay model, our value starts out large or far away from 0, and then over time gets smaller and smaller and smaller and smaller. So this would be an example of decay. This one also does not have an x-intercept, so this line never actually touches or crosses the x-axis. Our y-intercept is the same as above. Once again, it can always be picked out from your table, 0, 1. This one has the same asymptote as our previous equation. Our asymptote is right along the x-axis. This is a line that our function approaches but does not cross. So it comes down, gets very close to it but will not cross. Y equals 0. Horizontal line at y equals 0. And our domain and range are the same as well. So for our domain, it does point all the way to the right, and this, although it looks up, does point to the left. So we can either say negative infinity to infinity, or in set notation, all x, such that x is a real number. For our range, the lowest our line gets is to 0, but does not touch it, and then it's above that, bigger. So for our range, it'll be 0 to infinity, or you can write all y such that y is greater than 0. These are our basic growth and decay models for an exponential function. We can add, subtract, we can change numbers within the formula, within the function, in order to make it do different things. So whenever we graph this, we're going to graph negative 3 to the x plus 2. It's going to have the same general shape, but some things have changed about it. So one thing you might notice is that instead of pointing up, right, instead of being up here like both of these were, this one actually ends up going down instead. It does cross the x-axis, where neither of these cross to the x-axis. But it still has this very flat line, like we saw with these, this flat asymptote line. It's just at a different value. It's up higher. To graph it, we're still going to go second graph and plot some points from our table. So this one's on my graph, 2, negative 7. 1, negative 1, 0, 1, negative 1 and 1.6, negative 2, 1.8-ish. And so if you scroll up, you'll see there the values are getting closer and closer to 2. And this is where it'll eventually say 2, but it doesn't actually reach it. Your calculator just kind of gives up and rounds. But it never actually reaches it. It just gets so close to it that it might as well be 2, but it's just not quite 2. So when you draw this in, make sure to run right along 2, and then turn down and fill in the rest of the line. Our horizontal asymptote for this function is right here at 2. This is where our line is approaching, but not crossing as it comes up. Approaching, but not crossing. We did have an x-intercept in this case. It does not show up in our table. So if an x-intercept were to show up in your table, it would be where y is 0. But this kind of skips over that. So we've got 1 and then negative 1. So our x-intercept is somewhere between 0 and 1, right in there. But we have to figure out where that is. In order to figure it out, if it doesn't show up in your table, you press second, calculate, and we want to find a 0. If you haven't noticed, a lot of the things you want to find from a graph, you can find in the second calculate button. I want to find this point, so I'm going to go to the left side. So I've kind of, my flashing dot's on the point I want to find. So I'm going to press left a couple times. Now I'm on the left side. Enter. Now I'm going to cross over the point to the right. I'm helping my calculator narrow down where to look. So when I press enter, never guess, just press enter. It tells me I have an x-intercept of 0.6309. So my x-intercept is 0.6309, approximately. Our y-intercept always shows up in our table, and our y-intercept in this case is 0, 1. It's just a coincidence that they've all been 0, 1. That can change. So don't expect it always to be, but these three examples, they just happen to be. Our asymptote has moved. So we were able to move our asymptote up to 2. It has to do with this number by adding the 2 at the end. So where our asymptote was at 0 here, our asymptote here is at y equals 2. For exponential functions, our domain will never change. Our domain is going to be all real numbers. The reason is because we're allowed to input anything we want. It points all the way to the left, and it points to the right, counting for all values. So negative infinity to infinity, or once again, all x, such that x is a real number. For our range, for these, the whole line was above 0. It was above 0. In this case, our entire line is below 2. So we want to say from negative infinity to 2, don't include 2, or you can say all y such that y is less than 2. Okay, on the back, we're going to solve an exponential equation. So if you want to solve an exponential equation, we can solve it just like any other equation that we've solved in our calculator. We can graph the left and the right side and then find where they intersect. So I'm going to graph the left side, which is 2 to the x. I'm also going to graph the right side, which is 110. And I want to figure out where these intersect. Well, 110 is definitely not going to show up on my graph. So in order to do this, I'll have to zoom out. I might have to zoom out a considerable amount. We'll see. There's our one. Yep, our other line doesn't seem to be showing up. So maybe I'll zoom out again. I always try to zoom out first because it's a little bit easier than changing my window. Sometimes it'll work and sometimes it won't. Okay, I don't really see my first line, but I do see this. I think this will be enough where we can use second calculate intersect and just press enter 3 times. Ta-da! It worked. So 6.78 is what this is saying the solution is. Once again, to do that, I zoomed out until I could see the intersection point. I know we can't really see it, but it is there. We press second calculate intersect, which is number 5. And then it'll just press enter, 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 and it should give us the solution. So my calculator said 6.78135, so 14. So that means, bless me. That means that this is my value of x that makes this true. So let's check. Second quit 2 to the 6.7814 is about 110. Pretty close. So my answer to this question is x equals 6.7814. You can always do this whenever you're solving an equation. Graph the left, graph the right, and find where they intersect. It is a great strategy solving an equation. All right, our next question says, an entomologist monitoring a grasshopper plague notices that the area affected by the grasshoppers is given by this, where n is the number of weeks after the initial observation. Find the original affected area. So the original affected area is going to be when our weeks are 0. So n is the number of weeks. I want to figure out when we are at 0 weeks, which is n equals 0. So we're just going to do a with 0 plugged in. So I'm going to take 0, plug it into 1,000 times 1.15 to the 0, and that should give us 1,000. So 1,000 is our original affected area. That's our starting amount. This gives us the area that's affected by these grasshoppers, grasshopper plague, and in terms of n number of weeks. B says find the affected area after 5 weeks. So n's the number of weeks, so we're just going to plug in 5. We'll see if our value is increasing or decreasing. So 1,000 times 1.15 to the 5, 2011.3536. This is in terms of hectares. So you can see the affected area is increasing, as it started out with 1,000 acres, and now it's down to 2,011. So it is increasing in the amount. For this next question, I'm going to use the graph paper that IB gives you whenever you're taking your exam. So this is 1 centimeter graph paper. Every solid line is 1 centimeter, and they're going to tell you in some cases how to scale your axes. So this says draw a graph of AN against N. Let 1 centimeter equal 2 weeks. I'm going to make a little graph here. And 1 centimeter is 1,000 hectares. So we want to graph this. I'm going to type this in my graphing calculator, even though my numbers are going to be pretty big, because it's going to generate a table for me, which is nice. So 1,000, oops, go up here. 1,000 times 1.15 to the x power. Although the whole line would be off of my normal, oh, there it is, it's over there, off of my standard graph, it still generates a table which will help us graph it. So I'm going to go second graph. I need 1,000, and then it does increase pretty quickly. So whenever I scale this, I'm going to come over here. Actually, let's go like, fold it up a little bit, you can see. My x-axis will be my weeks, my y-axis will be my hectares, like this. Probably want to start with 0 weeks. It does say let 1 centimeter equal 2 weeks, so this would be 2, 4, 6, 8, 10. It says 1 centimeter is 1,000, so this is 1,000. This would be 2,000. 3,000. I'm not going to label every one. That's just kind of exhausting. So this is 5,000, 6,000, 7,000, 9,000. Okay. And then plot some of our values. So 0, 1,000 is our starting point. If I go 1, and then it's at 1,150. 2, 1,322. I'll just skip to 4, 1,749. So this would be every 200, 200, 400, 600, and there. 6 is at 2,300. 7 is 2,660. And I skip ahead to 10. 4,045. If we maybe go to 16 weeks. 12, 14, 16. And it's at close, right over 9,000. So it looks something like that. Okay. Would be our graph. Part D says how long will it take the affected area to reach 10,000? So if you look at your table, X is our number of weeks, so you can see at 13 weeks that's how many acres, 14 weeks, and so on. So at 17 weeks we've now surpassed 10,000. So for an estimated, we could say about 7 weeks. Alright, thanks for watching. Your Chapter 18 homework list is available for you on Canvas, so please look at that and get started. Thank you for watching again.